Swayam Prabha. Digital India. Educated India.
Hello everyone. In the last class, we discussed about divide and conquer recurrences, which are recurrences which primarily is used to solve problems by decomposing and calling its subproblems over lesser number of instances, and then by decomposing it and finally producing the answer. We have also seen that how such kind of recurrences are very useful in analyzing beforehand the solutions or the strategy that you develop for solving a problem. And we have seen examples from finding maximum in different ways where we split arbitrarily and we split in a tilted manner equally. And we saw that every time maximum finding takes n-1 steps. We go for find max and mean, have interesting observations there that if we split half in case of 2 to the power k number of elements, or if we split 2 elements at a time and n-2 in the rest, we get a beautiful answer which is 3 by 2 n-2, which is much less than 2n-2 in the naive case where we split 1 and rest, or maybe do the max and mean in 2 iterations. And also we see that the linear search in any kind of splitting, either it's a constant depth or it's a fractional, tilted, equal, it gives n number of comparisons to search an element in an unordered array. Though binary search gives us a very optimistic answer that why, and we understood that why we need to split in the middle instead of tilted fractional splits or multiple number of splits. Instead of one splitting, you can do multiple splits into subproblems. And also in a constant depth split, we do not get better answers in binary search. So the middle split gives us better. And finally, we ended in the last lecture with the sorting, different types of sorting algorithms by showing their efficacy in terms of the recurrence. Though we did not solve it, but we have seen a particularly interesting types of recurrence which is kind of a 2n by 2 plus some function. And in case of the final sort where we partition and then sort it, we also see 2n by 2. So it gives a fragment and a similar amount of fragment it tries to call, and then finally have a function to merge it. So in today's lecture, we will try to see the fundamentals and the formalisms or proofs that how we will solve it, how we will reason about these recurrences in a more formal way. To start formally, generally we have seen in all of these examples, one of the primary divide and conquer recurrence relation format is you divide n into b number of instances, assuming that for a large n is of the order of b to the power I, because then you can just converge by going into a constant or base condition. So you assume n equal to b to the power I and you divide it into n by b instances every time, and always when you divide you create a number of such instances, and your decomposition plus recomposition steps takes fn time as we discussed. So pictorially, if you go stepwise, what you are doing is that from fn you are giving a number of instances each having size n by b. So see how your number of computations here or the tn value of tn finally gets changed. So initially it was fn plus all the fn's returned by these set of instances you created first. It is a number of f a n by b. Similarly, this all again gives a number of f n by b square. It adds up. So finally, all these additions are your computation steps for tn when you go down till the end. And when you go down to 1 for each of these base cases, so all possible number of f n by b to the power l, a to the power l number of those will be added, and finally this is your merged answer for tn. So in a way, if we try to solve this generic recurrence, which we have seen an example in sorting, quicksort and merge sort, that it is 2tn by 2 plus function of an n. So that function of n in case of sorting we found it to be n itself, but the generic form is some a number of partitions of n by b size and some function to decompose and recompose. So therefore we need to have devise certain procedures to solve this equation based on how we unfold it. So as you have understood through this tree, which we call as a recursion tree, that we recurse or compute sub-problems and finally collect back the answer to get the final answer. Our unfolding process results this, because a t n by b produce a square t n by b square plus a f n by b. And this is your fn. In this way, if you go till b to the power I, where is your base condition gets met, because n equal to b to the power I, it will be a to the power I t b to the power I. And all of them will be added up as from j equal to 0 to I, a to the power j f n by b to the power j. Because if j is 0, then it is f n only. If j is 1, it is a f n by b plus a square f n by b square plus a cube f n by b cube, and so on. Now this term is 1 because n equal to b to the power I, we reach a base case. There are a to the power I number of them. What is a to the power I? I is log n base b. So a to the power I is a to the power log n base b, which is just shifting n with a. Okay, transferring n with a, which is n to the power log b base a. A to the power log n base b is equal to n to the power log b base a. So the first term is this. What is this term? Your I, as I have computed, because n equal to b to the power I we assume. So your I is log n base b. And we go from 0 up to, so this will be, this will be I minus 1, because see here the index here is 1 less we are getting here. So if I have a to the power j, this will be I minus 1. So that's why it is log b. So this is a mistake, just correct it. This will be I minus 1, it comes as log n base b minus 1. So now see, computing Tn means we need to approximate what this term will be. So that will be my answer for Tn finally, if we want to compute it. Now let us try to have some cases over it, because we are seeing this as n to the power log b base a. So there are three ways in which we can bound Tn, that either we could think of this function or the function fn is bounded by this n to the power b log a, then we will see where it happens. So depending on this particular n to the power log b by b, a base b value, the function nature depending on greater than, less than or equal to this value, let us see what this term reveals us. So here we go with case 1, which says that fn is less than n to the power a log b, that term, minus epsilon for some d and epsilon greater than 0. So what does it say? It says that fn term is obviously less than, with respect to n, it is less than this. Because it means that if you take limit fn by this term, it will result you to 0, because this minus epsilon, it is less than equal to that. Okay, so therefore fn function is dominated by this function. Always the curve for fn after a certain point will be dominated by n to the power a log b. That's why we are getting minus epsilon, this n to the power, this thing is dominating. So what happens here? Let us expand this one. I know fn by b to the power j. If I put it this inequality here, it becomes n by b to the power j log a base b minus epsilon, and d is putting out here, because fn is less than this, so fn by b to the power j is less than dn by b to the power j to the power this. So just I have put fn b to the power j here with a less than equal to, assuming this relation. Unfolding this one will say that what I will do here is that, you see, this is dependent on j. That means n to the power this whole term can come out because there is no j here. So only thing remains is a b to the power epsilon by b to the power log a base b to the power j. Because this is minus epsilon, I just put a b to the power epsilon multiplied both sides. What is this term? B to the power log b base a is nothing but a to the power log b base b. B to the power log a base b is nothing but switching a and this b. So it means it becomes a. So this becomes b to the power epsilon j. Only I changed here. The rest of the thing remains the same. Now when this happens, it means that you are going from 0 to this. This is a GP series. This is this minus 1 by b to the power epsilon minus 1, because some term to the power j in increasing in geometric progression, if you add it, you get this one. What is this one? Now you see this one, if you simplify it, this term. So this, how do you simplify it? Epsilon, you put this as b to the power log n base b whole to the power epsilon, because it's multiplication, you can put it all to the power epsilon. What is b to the power log n base b? It is n, because you can switch n and b. So n to the power epsilon is this part, minus 1 by this. So now it says that it multiplies with n to the power epsilon to get this back. Rest of the term is minus and this is constant. So you can bound it by d into n to the power log b base a. So what does where we started off with? We started off with my fn is upper bounded by n to the power log b by a. Strictly it is upper bounded in that, because epsilon is greater than 0. So I reach that my this function will also be equally, but I mean upper bounded or equal to n to the power log b by log a base b. When I say upper bounded or equal to, it means that it is, if it is a constant and this is equal, it is this function and this function growths are same. Otherwise it is upper bounded by this. The second condition, we will just change this one. We will see that fn is comparable with this function. So finally, when you put this one, the final result is this plus d is just the final results I am doing. So since these two are the same, it's just this less than equal to c into some constant c into n to the power log a base b. So if I have this kind of condition going, I get my Tn will be also bounded by this. Case 2, as I just suggested, that we will have, instead of strictly bounding down this function, we will say fn, the growth of fn is comparable with this function, that is these two function grows equal. So when we say these two function grows equally, it means that, see here, we have this as our previous computation. So we are trying to approximate this part, the gn part. So when we do that, again that function starts off with, take the less than equal to thing. When we take less than equal to, here we n by b to the power j, I just replaced it. No epsilon here, so our job is simpler, because we could take out n to the power log a base b, and then this is a by b to the power log b base a to the power j, which is basically a by a to the power j, which is 1. That means this term results log n base b, which means this is equal to this into log, we can less than equal to do it, log base n base 2, because b is a constant. And b is a constant, and obviously b is more than equal to, I mean it is 2 or more, or it's a constant. Therefore, you see that now I got, similarly in this scenario also, I can upper bound it by such kind of a thing. So we can easily say that this, if we replace gn here, since you bound fn, growth rate of fn as n to the power log a base b, you can also bound tn as the growth rate of tn as n to the power log a base b into log n, both sides. Okay. The third is that instead of, so we started off with fn growth rate being lesser than n to the power a base b, and just bounding it over that equal type of growths, then it is also equally bound in this way with a log n term extra. Now it is not bounded, where we assume that fn is more than n to the power log a base b. So it is n to the power log a base b plus epsilon, which means that it is fn is I mean, this is a lower growth rate function than this one. The n to the power log b by a growth rate is less than fn. So fn grows faster. So since fn grows faster, I mean, how fast? That's why we need to have this sub problem with a bound assumption that a of n by b less than equal to k of n for some constant k less than 1. So when we do that, for all sufficiently large n, so remember here sufficiently large n means n tends to infinity. So same calculation reveals that here I have assumed AFN by B less than equal to KFN, which means that this is less than equal to KFN, AFN by B less than equal to K by AFN. So if I do n equal to n by B, this will be this transform here. So therefore Fn by B square is less than equal to K square by A square Fn. Similarly, Fn by B to the power j is less than equal to K by A to the power j Fn. I looked at this term and tried to have this inequality going. Do it here, put it back, Fn by B to the power j as this less than equal to inequality wise. So what does this mean? This means is just K to the power j Fn, and now again for sufficiently large n I can do this to the infinity and I get a constant into Fn. What does this mean? That G is actually growth rate is equal, it's bounded by constant into Fn. You can also show the other way also, that there is since K is less than one constant and exact powers of B, we can conclude that Gn is growing as same as Fn, and if we substitute in this equation, we will get this calculation as Tn is of the same growth rate as Fn. Because Fn is greater than equal to this one, this one is this, so you can do this way. So now the point is that what does these three reveals us? These three is a very nice algorithmic analysis techniques for divide and conquer recurrences, which lead us to a famous theorem called master theorem. Those who are doing the algorithm course may also have seen this theorem and used it somewhere, but here lies the proof, because why these three conditions and why this thing matters. So we have one inequality which is upper bounded by, in algorithmic sense you have seen it this way, that it is upper bounded by this. Then you can see it as Tn equal to O of n log A by A base B, n to the power log A base B. If it is sandwiched between or growth rates are same, then I just have n to the power log A base B into log n being sandwiching Tn, that is these growth rates are similar equal to Tn. So we talk it as this way. If Fn is theta of this, then Tn is this. This is the brown part are deviating from discrete math into algorithmic domain, where we go for asymptotic complexity notations. And when this overshoots, then for certain conditions of Fn, we got that my Tn is actually sandwiched between the Fn growth rates. So therefore we say that if it is sigma, means it is crossing this growth rate, it is higher than this growth rate, and this function holds, then Tn equal to theta Fn. So this is called as Master's theorem. Now you can see that I can put in our sorting example, go and put back A equal to 2, B equal to 2, Fn equal to n. See which of the cases you find out and get the results that what is your bound. Obviously you will see there that if A equal to 2, n equal to 2, the case that you will find is case 2 and Fn equal to n. Just try and check it out. Here are some examples for you with using those recurrence. So here Tn equal to 9Tn by 2 plus 2n cube, and the base condition is 1. Here clearly A equal to 9, B equal to 2, Fn equal to 2n cube. And hence you can see here is that Fn is 2n cube less than D into n to the power this, because this is more than 3. So epsilon greater than 0, and there exists some value of D. I have chosen 3, but it's arbitrary. You can just upper bound it. So therefore when you say this happens, then you say it is upper bounded by log this B base A, B is log A base B, A is 9 and B is 2, so this is upper bounded by this. So we call it in algorithmic sense as order of this. This is the example for case 1. The example for case 2 goes in the same way, that you have 8Tn by 2 plus 2n cube. Now check for A and B, it is 8 and 2 respectively, Fn is the same. So now you see that log 8 base 2 is 3. Now this is n cube is comparable with this one, 2n cube. So you can have D1 and D2 value so that you could sandwich 2n cube, right? Greater than and less than. If you select D1 equal to 1 and D2 equal to 3, so 2n cube is sandwiched between that. So in that case, we have our answer that it is n cube, that is n to the power log 8 base 2 into log n will be sandwiching Tn. So it is called theta n cube log n. This is our example of case 2. Just reduce the a by another one. 7 Tn by 2 to n cube. Here a is 7, b is 2. Now you see that 2n cube is greater than equal to, because its n to the power order is now not reaching 3. So epsilon must be greater than 0 to match it. Therefore, this growth rate is definitely more than the original n to the power log 7 base 2 growth rate. When that happens, I need to check 7f n by 2 equal to this one. And when this is less than k into my function, so af n by b, this is af n by b is less than equal to k fn for some k value less than 1, because it is 7 by 4 n cube and this is 2 n cube. So k can easily go to 7 by 8, up to 7 by 8 to make this happen. So this is less than 1 k exists whether this happens. 7 by 8 or more can make this thing satisfiable. Now when this is the case, then you say that fn will sandwich t. So Tn equal to theta n cube in that case. So here are 3 examples of Master's theorem, but since you know the proof now, you can easily now estimate that how we proceed and start from a generic recurrence and can prove the same thing too instead of just using the formula. That's what we do in the last lecture when we show you the examples and expanded it. It's just expansion is nothing but summation of that function. And since our summation has a closed form, we get the answer very easily. If the summation taking was a little bit difficult, then we might have used this kind of mechanisms of master theorem to solve those. So this is one kind of split that we discussed, that it is of n by b size and a number of them. There could be other split as well. So in the example we have seen not only every splits are equal is only our recurrent divide and conquer solution. There may be splits which are unequal in and divide. So you split in alpha 1 into n number of partition as the first partition, alpha 2 into n as the second partition. And see, there are no bound between this alpha 1, alpha 2 up to alpha k, because some partitions could also have, fragment of the elements be equal. It is up to you that how you want to solve the problem. I want to solve a problem by making all the elements here and here common except one. You may want to solve a problem by making elements here disjoint. But it is up to you how you want to solve the problem. So the generic form of recurrence will say A1 instances of T1 alpha 1 n size, A2 instances of alpha 2 n size, you are calling it recursively. And finally this. So this is a recurrence that we get for unequal sized, your split size is unequal, and finally you then decompose and combine using Fn to get the answer. Instead of reducing cluttering in the slides, let us solve a small variant of this where we say Tn equal to A T alpha n plus Bt beta n, where alpha beta are fractions. So first of all, let us see if we expand or form the recursion tree, how does it expand? Then we will show in an example that exactly what do I mean. Though this theory may seem a little bit cluttered because of these expansions and lot of algebras inside it, but the examples will show you that how it is being used. So obviously, if you expand it, this formula, you will get the first term will again reveal you At alpha square n and plus Bt alpha into beta n, because your n is now alpha n, so beta into n means beta into alpha n. So therefore this term will reveal 1 a square or T alpha square n and 1 abt alpha beta n. This term will reveal 1 abt alpha beta n and 1 b square T alpha beta n, again as a recursive call. For Fn, this term, the Fn that will be revealed by this term is a f alpha n, and the Fn that will be revealed by this term is again f of beta n, which will be b into f of beta n. See how we are expanding. This looks like a nice format. If I go along one side ahead, it will be a nice format. It just looks like a binomial kind of a format where it is 3c0 a cube t alpha cube n, a square b, alpha square b n, and so on. And this function is just, everything is perfect, but one less in the nc0, it is n minus 1 c0 it starts, and every possibility it just adds on. So eventually the final function may look horrible, but it's nothing but we are just expanding it as a to the power l plus 1 minus I, because we are giving here l minus 1 in order to cope up this, because this has the maximum index 1 less than this. So this is just the closed form equation that we have in summation format about the whole thing. This is what do we mean by the expansion in the recurrence tree. And finally what we have to understand is that is after L step, suppose this reaches to base condition, where does this value approximates to? Because that is our Tn. We need to compute Tn. Now in order to compute Tn from this formula that we just expanded and found out, we can see that, let us assume that alpha to the power m1 n equal to 1 and alpha beta to the power m2 n equal to 1, and assume that alpha fraction is more size than beta fraction. Now if this is the case, you can easily see m1 must be greater than equal to m2 to have these two relations going. What does it suggest? It suggests that the path in which you fragment n into alpha n, alpha square n, alpha cube m and reach the bottom position will be longer than the path you fragment as beta n, beta square n and so on. Because since alpha is a higher fraction than beta, therefore alpha n must be higher number than beta n. So therefore when you go n to a subproblem alpha n, then alpha n to a alpha square n, that route is much longer or have much depth in recurrence tree than the other route. So the approximation says that why not we say that everything will be unfolded T alpha 1n, whatever be the base case we formulate for T alpha 1n, and we just unfold it till T alpha 1n. Okay, and then solve it. So I'm not just going details into this computation. Just from here, if you unfold it till alpha 1n, you will get exactly this as your less than equal to, because that is the worst you can get to. Some of the branches might finish earlier reaching the base. See, m1 is greater than m2. So you have not, I am thinking here everyone reaches till depth m1. Since m1 is greater than m2, the right-sided branch, if you say the beta-sided branch will always finish earlier. But this is an upper bound, that's why I am approximating it over an upper bound. Similarly, I can approximate it with the m2 branches in the lower bound side. That everything will be, Tn is obviously greater than if I finish it at the m2 level. Whatever be the recurrence tree I finish at the m2 level, if I try to compute all the actions being done till that point, I will get here. So just this is a rolling calculation from here. I mean, it looks a little bit cluttery, but you can just have it in your own notebook and do it. The lessons learned is that since this kind of unequal divide recurrence has a different unfolding parameter, so you cannot just unfold and try to compute, because sometimes this particular summation you do not have any closed form for it. So you try to upper bound it somehow, and try to upper bound it by having an upper bound over here, and then you try to see how much close you can upper bound it. And sometimes some obvious recurrences which you can upper bound it we can mathematically, by using mathematical induction, we can prove the answers very successfully, may be upper bounded to a little gap between them. We will see one such examples, but you can also study, or you can also find some closed form expressions depending on f of these functions, as we do in the master theorem. That if it is upper bounded by this form, what happens? If it is growth function is equal with respect to this form, the f growth function, what happens? The same way we can study this one as the generic sense. It's a good algebraic exercise for you if you proceed. However, the thing that we want to mention is to give you a bound or an answer bound for such kind of steps. So let us come back again with the linear such fractional split thing, where in mathematical induction we proved something, and we say that it is an plus b, where ab equal to 1 and 0 respectively is one of the answers we can get. However, in recurrence tree format, what you do is that every time you split n by 3 to n by 3, this is n by 9 to n by 9, this also gives to n by 9 for n by 9. So this way it goes on. Now the point that I want to mention, if you enumerate the depth in this part, it will always be less sized than you enumerate the depth in this part. Because see here n is reducing to 2n by 3, which is obviously more than n by 3. It is reducing to 4n by 9, which is obviously more than n by 9. So therefore this depth converging till the base case points will be much higher. Now I can upper bound it by saying that the number of leaves there until this depth, the computation that I do till that point, the decomposition plus decomposition and all the base value computations, I add upon, that will be my upper bound. So here you see the computations are 0, only it comes from here. If you reach base, you get 1. So that one computation pushes up. So the number of base level computations is your answer in the final case, because that computation get pushed up. So therefore you can upper bound it by the longest size branch. So n to n by 3 to 2 square n by 3 square to 2 cube n by 3 square up to it is 1. So it will be 1 when your 3 by 2 to the power k is equal to n, which means that at this level, after this level, everything should have been in the base. The longest branch reaches base means everything should be base. And if I see that everyone is there in the base, I get this as my upper bound. Unlike here, the lower bound side will obviously tell you that your lower bound will obviously be n base 3, right? Because you are doing n by 3, n by 3, n by 3 and you're going till the base. So this should be 3, there is a mistake, this should be log 3 base n. So hence this will so this will be log 3 base n, this will be n to the power log 2 base 3. So see here, the point is that though we found out this is kind of a linear, but you see that it is n to the power log 3 base 2 and sandwich between log 2 base 3 by 2. Okay, so this is somehow we have upper bounded and lower bounded this based on the unfolding of the recurrence tree and the work done till the base point. If you unfold the recurrence tree on the strictest possible way, that is the lowest possible depth you will unfold and cut the rest of the tree, that will be your at least those many works you have to do. If you go by the most lengthy path, then if you reach the base, then everyone else will finish. Now if you add up all, that will be your upper bound. So I just have those two bounds to bounds n. So that is why we see here that in this kind of a fractional split, another approach of solving this recurrence instead of having a closed form equation, if you can do it with respect to some fn or some function, that it is better. But if you cannot do it, we also try to give an upper bound and lower bound approximation, and in this way we also try to produce an answer to it. So as per the strategy of our lectures, we usually give one exercise to a concept which is new to you. So this is one exercise. Instead of having nothing in the decomposition and decomposition value, I just put a log n there. The rest is the same. You just do this and see how you can bound it. Or you can form a closed form expression. For that, you need to exactly solve these equations in general. So here also in our example, our alpha is 2 by 3 and beta is n 1 by 3 because we assume alpha to be more than beta. So this is one of the approach we can follow for divide and conquer based strategies. The third thing that we discuss is a constant depth divide, where we will assume A as a constant and we will assume that one sided of the fraction or the partition or the split will be of A size and the other side of the split will be of n minus A size. And we have seen that for n equal to 1, this is constant. Now, if you remember this kind of from the earlier lecture, that this kind of constant depth partitioning we usually do by taking an average, because A is equally likely to partition in any position. So therefore we do it by choosing A from 1 to n minus 1 anything. So this means that we will average it out over everything here. If you remember, we average from C equal to 1 to Cn minus 1. So this means you compute here T1 plus Tn minus 1, T2 plus Tn minus 2. Similarly here Tn minus 1 T1, Tn minus 2 T2. So you compute T1, T2 everything twice. So 2 by n minus 1 this term. Plus Fn equal to n minus 1 times you compute and n minus 1 cancels. So it is this. So it gives you n minus 1 into Tn, because you put this term here equal to 2 of this plus n minus 1 into Fn. You multiply everything by n minus 1. Now the strategy was they put n equal to n minus 2. The similar equation reveals just putting n equal to n minus 2 everywhere. N minus 1 everywhere, sorry. Putting n equal to n minus 1 everywhere. Subtract second from the first, so 1 minus 2 will result this minus this equal to this one. Okay, so here just one thing will be that, so this will be n minus 2. This will be n minus 2. This is a mistake. This will be n minus 2. So when you do it, you will see that there is, then we will try to find out a pattern of the whole thing. When we can find a pattern of the whole thing, our job simplifies, because now we will try to do n equal to n minus 1, n equal to n minus 2, write everything and then try to add up, if you remember our example. So this is the equation that we formulated. We just write everything and then add up. Because adding up means cancelling these two terms, cancelling this term and this term, cancelling this term and here. Similarly this, similarly T2 and here. Adding up this means 1 by n Fn, and this whole coefficient of Fn minus 1 and this one will give me 2 into 1 by n minus 1 minus 1 by n. It will give a very nice structure finally. And we will reach at a base because everything cancelled except this term and this term. Okay, it's a standard strategy that wherever we found a recurrence, we average it out, take n equal to n minus 1, just put the equation as n minus 1 Tn minus 1, this minus this equal to this, and when you put up everything here, this will be like this. Okay, I just have a step jump. I do this minus this, and for Tn minus 1, I just put it in this side, it results this one. Because this minus this will keep 2 into Tn minus 1 term intact. And then have a division of n into n minus 1 all sides. This will give you this. This structure you can usually do it in a better way. Once you came into this point, then write for every n into n minus 1, try to solve it by adding. You will get a beautiful form which gives you Tn equal to, this is your C. So C plus n gets multiplied everywhere. Fn into this, 2 into n into summation of this. So if you find it difficult to understand, please do it in your own hand. It will be very easy. Otherwise, I can give a simple examples of that quick sort we got. Arbitrary partition and arbitrary size partition, and then n for the final. Taking the partition into two parts. See here, if we use the formula, it will be, this function is n. So therefore, you see the formula here, it is fi. So Fn equal to n, that means Fi equal to I. So you have to solve this one. Your C is 0 because your constant is 0. This is n plus this one, and therefore n plus 2 into, if you solve this one, it is nothing but 1 by 2 into 3 plus 1 by 3 into 4. If you take your I is into 2. So 1 by 2 into 3 into 2 means 1 by 3. Then 1 by 3 into 4 into 3, I becomes 3. Means 1 by 3 into 4 into 3 means 1 by 4. 1 by 4 into 1 by 4 into 5 into 4. So I gets cancelled out. So it becomes 1 by 3 plus 1 by 4 up to 1 by n. So therefore it is just 1 by 1 minus I if your Fn is equal to n. So it is just this one. Hence, it becomes this minus 1, and this is from an harmonic series. You know that this series comes up into ln n plus gamma minus 1 by n, where gamma is just a recurring fraction like this, which is Euler-Mascherani constant. But the interesting point is that this is just in the same growth rate as log of n, which is very interesting that this kind of sort gives you log of n time even if you arbitrarily split 2. Now use the master's theorem and take that if it is a equal split, how much time does it take? You will be amazed to see that it will always be comparable with n log n. So therefore, quick sort and merge sort, the constant split, arbitrary split different location-wise split, all of these things doesn't matter. I leave it to you to analyze whether if I split equal sized multiple paths, multiple fragments, how does the analysis go? As we have done it for binary search. How does it go for any kind of merged sort or quick sort thing? So an assignment for you, a little bit variations of this n. I gave you n log n, how it will come. Just try it by your home, either using this formula and try to find a closed form, or you go by this rule. Try to find here a particular recurrence format and then go by this rule. Instead of just writing it this way and adding and cancelling terms, you can also consider Tn by n equal to Sn. You can consider a different function Sn which is Tn by n. This is Sn, this is Sn minus 1, the rest is same. And if you do it that way, you will find finally when you get the Tn, when you finally get the Sn, you have to multiply with n to get the Tn. Okay. So a prime example of such kind of a thing we will eventually see when we study the concept of change in variables. So see, what we are doing here is just change in variables, because we have a complex term here which is a recurrence plus including a function. We want to change it and make it smoother with a different variables or different computation. However, change in variables depict us that suppose we have a variety of recurrent form which is not like we studied or formulated. 2t root n plus log n. So it's not n by b format, at n by b, we are not seeing it anywhere. So what to do about it? Assume n equal to 2 to the power 2 to the power m. We can always assume something for n. If you assume this one, then what does this becomes? Base condition. If n equal to 2 to the power 2 to the power m, then m equal to 0 will be your 1 as a base condition. M greater than 0 will be your this condition. What does this condition be with m? T 2 to the power 2 to the power m equal to 2t 2 to the power m minus 1, because it is 2 to the power m by 2, which is 2 to the power m minus 1. What is log n? Take the log, it's 2 to the power m. Now it looks very simpler, because this, if I assume it to be Sm, then this will be my Sm minus 1. Which helps, because now Sm equal to 2 into Sm minus 1 plus 2 to the power m. And S0 is 1. Which means, now you can easily go by this way. So this will be 2. 2 into Sm m minus 2 into. This one is 2 into Sm minus 2 plus 2 to the power m minus 1. So that will come as 2 into 2 to the power m minus 1 when it come out, and this 2 to the power m here. So this will be like this, if you add this 2. So here there is one thing missing. It is 2 into Sn minus 2, because this 2 will remain everywhere. So somehow then if you go here also, you will get this point. You go here 2 into S0, so it will be 2. So finally you reach here with the 2 plus m into, so all this is 2, because 2 into S0 everywhere. So finally Tn equal to T 2 to the power 2 to the power m is your Sm, which you got it here, where your m is basically log n, because log n is 2 to the power m, so log n is m. So you replace log n and 2 to the power m is log n, so the final formula you get is, this will be 2 plus this, because the answer here is 2 due to all the 2 coming here. Okay, so this is what do we call by changing of variables, because you have something which is directly cannot be formulated using your divide and conquer recurrence format, or you cannot unfold it in that manner or give a closed form formula. So indeed what you have done is that you take and have another variable into that and try to push it there. Unlike the previous case where I combined a recursive function as Tn by n itself, here I change the variable. Instead of the recursive functions to be modeled by some other function, I change the variable. So this is change of variable, and this is just mimicking it with another function. So this is also a function of this. This is also a function of m, because m, this is a function of 2 to the power 2 to the power m, indeed a function of m. This is 2 to the power m minus 1, since only m changes, is indeed a function of n minus 1. So these two functions we can mimic. Finally, this gives us this kind of an answer. So as always, we can now again pose a little bit of tricky problem here. So here, if you see, the catch is you have to come down to an uniform position, right? How do you come down to an uniform position here? You divide everything by n. What do you reveal? Tn by n equal to t root n by root n plus 1. See, Tn by n, T root n by root n is just, I can assume it as Sn equal to S root n plus 1. Now you are in this kind of a format. Sn equal to S root n plus 1, same procedure. You go ahead only with your constant is 1 here instead of log. Simpler. So in this lecture, we have summarized that what are the general techniques of solving different types of divide and conquer recurrences. We started off with master theorem, which is basically fragmenting the subproblems into equal parts or equal fragments and a number of those. And we have found out there are 3 certain kinds of cases which arrive, and we could derive that final number of steps can be bounded by those 2 cases. Then we have also seen how we have unequal fractional split recurrences, and where do we try to bound the values of the recurrences by unfolding in the recurrence tree, the upper bounded by the lowest possible depth we can reach and everyone reaches there, assuming it to that sense, and lower bounded by the lowest possible depth, the lowest possible depth or the height we could reach up to found the base is by which we would lower bound the problem. And we have seen two examples of having those. Finally, we have also seen how the constant split things we could average it out and then make a solution by adding them up and then storing and then manipulating over it to get a recurrence and finally getting a solution. And there are certain things called change of variables, where your variables might not directly appear as n by 2 or n minus 2, something like that. It may be a function of n where you need to change that functions to a simplified variable so that you could directly apply those. With these concepts, I would like to tell you to go back to all the examples in the previous lecture which we have formulated and try to give a thought which kind of recurrence mechanism it follows, which kind of formula it will follow as per our generalized formulation rules, and try to apply those rules and solve it again. And see the beauty of recurrences in many other applications of computing and other areas, where you solve problems in terms of subproblems and finally converge it by seeing whether your recurrence give you good results or not. And in this way, you could find out your efficiency of the strategy using this kind of analysis by divide and conquer technology. Thank you.